Okay, hello again. We're going to go over exponential functions. These are functions that have a variable. It's not like x to a number like x to the 2 or x to the 3 where the number is up in the exponent, but the variable is the base. Exponential functions those would be called power laws. An exponential function is a function where the variable, in this case it's time, t is the variable, where the variable is in the exponent. So it's a number like 2 or 3 raised to some variable amount of, in this case, time. What that means is that you're going to have some starting amount of something, and then you're going to multiply it by a number by so many repetitions, so many times. So let's say I'm going to double my starting amount. Well, if 6 units of times have passed, then I'm going to double it 6 times. If 3 units of time have passed, I'm going to double it 3 times. So that's kind of what we're talking about. So you can kind of think of this as something that gets multiplied by the same number over some period of time. And as time passes, it keeps getting multiplied by that number over and over again. So those are called exponential equations, and it's a very fast rate of growing. This models growth, like bacteria growth, population growth, growth on money. We've seen a little bit of this already. And we'll see soon that it can represent decay of things doing the opposite of growing, but actually diminishing by a factor. So you're multiplying. And in fact, when you decay, it's division. And we'll get to that. But right now, we're looking at exponential growth. So let's say that, I'll try to do a little, I think I'm centered here. So let's say starting with 25 things. They double every 12 hours. How many are there after 4 hours? So that's the question. Okay, the way you would do this is you want to know basically how much is there after a certain amount of time. So you want to find this population after so much time has passed, time t. So you take your starting amount, and that's your first number that's out front that just multiplies this whole thing. So my population after so much time will be the starting amount times, let's see, it doubles, so that's going to be a factor of 2. I'm going to multiply by 2. How many times? Well, it doubles every, let's go over this for a real quick second, just what an exponent here would do before we finish this question. Well, what if no time has passed? What if t is 0? Well, it doesn't matter what we divide by. Anything, 0 divided by anything is 0. So if no time passes, if we're at the starting time, we'd have this. 25 times 2 to the 0, because no time has passed. There have been no times for any doublings. Okay, well, that means 2 to the 0 is 1. If you double, never. If you don't double, you're stuck with what you have, so you're stuck with the starting amount. So anything to the 0 is 1. So if no time passes, you have something raised to the 0, which means you're just multiplying by 1. You stick with what you have. So after no time has passed, you have the starting amount, which is 25. Okay, so what if, so if it doubles every 4 hours, what happens when 4 hours have passed? Well, you have 4 hours have passed, divided by the amount of time it takes to double. So that's 4 over 4. That's 2 raised to the 1, which means you're multiplying by 2 once. So that's just 25 times 2. This is just 1. So you get 25 times 2, so that would be, your answer would be 50. That's after 4 hours have passed. Oh, I'm sorry, I read that wrong. This is 4 hours have passed, and they double every 12 hours. So I guess I should have said if it takes 12 hours to double, and after 12 hours it will double once. I should have said that. So you got 1 here. 2 to the 1 is just 2. So after 12 hours, if it doubles every 12 hours, you'll have double what you started with, so you'll have 50. So you still have, it doubles every 12 hours, so you put the amount of time that it takes to grow by this factor. The factor is 2, it's doubling. You put the amount of time it takes to double underneath on the exponent, and then you put the amount of time that has passed up top. So 4 over 12, which is 1/3. So you don't do a full doubling, you do a third of a doubling. So what does that mean? Well, let's figure out what that means. So I have, I have 2 raised to the 4 over 12. I gotta use parentheses here, so that 4 over 12 is in parentheses. 4 divided by 12 is a third. But if I raise 2 to a third, I'm going to press enter. That'll give me this factor. It's not quite a doubling. It's almost like increasing by 25%, maybe 26%. Okay, so that's my growth factor. That's 2 raised to a third. And then I'm going to multiply by the starting amount, and I get 31.5-ish. Okay, so let's say I'm counting cats, or I'm counting, scoops of ice cream or something. Or let's say, things that come in units. So I'm counting people, whatever. So I don't want to count fractional units. So 31.5, it's not quite 32. I'm going to round down every time here. So I'm just going to say, okay, after 4 hours have passed, I would have 31 things. That's how you set it up. So let me do a different one, just so you get sort of a feel for it. You start with 112 things, which triple every, let's say, 4 hours. How many are there in, let's say, 15 hours? Okay, so I'm going to say that, well, let me first write the equation. I'm going to have my population will be the starting amount, 112, times, the factor is 3 because it triples. And I'm going to say the function is t over 4 because it triples every 4 hours. So if I put a 4 up here, I would get 3 to the 1, which is 1 3. So I would have 336 in 4 hours. But actually 15 hours have passed. So, well, every 4 hours gives me a tripling. So 15 divided by 4 would be what I raised my 3 to see how many times I multiply by 3. And it's going to be a fractional amount. So I'm going to say, let me pull up my calculator again. So I'm going to say 3 raised to the 15 over 4 times 112. And I'm going to get, in this case, whatever that was, 6,893. So that's how the exponential growth will work. So let me show you your homework here. Yeah, this is good. Done. Okay. Blah. Okay, so I have a population which increases by a factor of 5 per 16 units of time. So my factor is 5. Let me see if I can do this. Okay, so I will start this again. I now have a different question. My population increases by a factor of 5, so I have some starting amount, times 5. And it increases by a factor of 5 every 16 units of time. So I'm going to put the 16 down here. And it's estimated that the population in 2000, that's my starting year, was 1,000. So I'm going to put 1,000 here. If that's okay. Now, write the function that models the population t years after 2000. So if 2000 represents t equals 0, so if in the year 2000 I'd put a 0 here, and I would just have 5 to the 0, which is 1. So at the year 2000, with the 0 up here, I would have 1,000. But they want to know it as a function of time. So I'm just going to put a variable t here, and that's what I would put for my answer. So the answer we're looking for here is 1,000 times 5 to the t over 16. So that's all you got to do. You just have to plug into this formula. I'd recommend writing this down so that you remember where to plug things in at. And then, let's see, use the function from the, what is this? Use the function from part A to estimate the size of the population in the year 2010. That's 10 years after the thing begins. So I would put a 10 here. So instead of t, now I'm going to put a 10. So it, whoops. Okay, so let's pull out the old trusty calculator. And I'm going to say, oops. We're going to say, so I have 5 raised to the 10 over 16. There we go. Times 1,000. And I will have, I'm going to round down, 2734. Is that what they want? That is what they want. So that's how you do those. And you'll have 5 of them that are all pretty much the same type of question, just to make sure you know how to do them. Okay, so that's the first type of question. Good.